All right. Since we already done with chapter 17, uh, today we are moving to chapter 19 on acids, bases, and salts. Of course, acids and bases are a very important, materials that is important in chemistry and important also in our lives, because most of the food that we eat, the acidity and the basicity of that is very important. And one of the things that we usually measure is the pH of the material, and that is, it depends on the concentration of the hydrogen that produced from the acid, and that's of course determine a lot of reactions. So that's why this is a very important chapter. The chapter is divided over 5 sections, including the one which we will, inshallah, offer today, and that is on the acid-base theories. This is going to be an introduction to the definitions of acids and bases in general, their properties and how we define them, and what are the theories that put together to define each one of them. Then moving to section 2, we're going to talk about the acidity of compounds, and that is by measuring the hydrogen ion concentration. And then in section 3, we're going to talk about the strength of acids and bases and how we can deal with that. Then the last thing, or the one before the last, is the neutralization reaction. That is the reaction between acids and bases usually produce salts and water. And for that reason, the last section is about salts in solution. The one which is produced from the reaction of acid, or the neutralization reaction between acids and bases, is going to have certain properties that we have to look at. So that is, as usual, an overview of the whole chapter and how we're gonna run it, inshallah. All right, starting with today's lecture, which is on the acid and bases, or acid-based theories. There were 3 theories that put together along the history, that is defining acids and bases. The first one is what is known as Arrhenius theory, and that is the basic one, or the first one to be proposed. Then there was another one after that, which is the Bronsted and Lowry theory. This is defined, the acids and bases in a little bit different way. And the last one is the Lewis acids and bases, Gilbert-Lewis theory. Now, what is good about these theories is that in the past, if you remember, when we talk about several other theories and other topics, we used to, like if you remember when we talk about the atoms, like Bohr model, then after that, the model which comes after that, what is Rutherford has done, and so on, everyone contradicts the previous one, or override, so to speak, the previous one. But in this case, all these are just expanding the definition. It's not contradicting the previous one. So anything that is defined under Arrhenius is acids and bases that are with a limited number. Now, the second one, which is Bronsted and Lowry, came to become more general, to include the ones that are in the Arrhenius, and added some more that were not covered under the previous definition. And the last one is also even broader definition of that. So they are not contradicting each other. They are just expanding the number of acids and bases that can be defined under these theories. Starting with that, we need first to look at some of the properties. These are general properties, not necessarily to be memorized or anything, but we know that acids and bases, they have a very distinct properties. They have special properties and features that are not found in any other material. Like, for example, when we eat our food, some of the food which has the tart or the sour taste, that is usually due to the presence of acids. Also, if you make an aqueous solution of acids, whether it is strong or depending on the kind of acid, it will make a strong electrolyte. Now, what does the electrolyte means? It is a solution that can conduct electricity. due to the presence of iron. Any material that you dissolve it in water and has positive and negative ion becomes electrolyte, which means that if you connect it to electricity, it will conduct it through it. Acid, causes certain, dyes called indicators to change their color. And that's the way actually we differentiate between acids and bases, by using the litmus paper. The litmus paper is basically containing an indicator, a material that is called an indicator. It changes its color upon reaction with both acids and bases. So in the case of the acid, yeah, blue and red, that is right. If it is a red one, then that is an acid. If it is blue, then that is also. In addition to that, also, they're not necessarily the litmus paper. We have many other indicators that they will change their colors. Like, I will give you the most famous one is the phenolphthalein, for example. If you remember doing that titration experiment where you add the phenolphthalein to the base and it is pink or kind of purple, but if you continue adding more acid, then it will become colorless, and that is depending on which is the material. Anyways, this is just a general property. We will go into some details when we discuss the how to determine their concentration using the titration. Also, many metals, they react with acids, and that is most of these acids, they produce hydrogen gas, and they, in most of the cases, they are vigorous reactions. They react very very fast. As how melting point or boiling point? Well, you can measure it. I mean, I don't know how the question is related, but measuring a melting point has a method to do that. You mean in general, not to measure it? Well, we have discussed that previously when we talk about acids and organic compounds in general. So here we're talking about you specifying the organic acids, because there's some organic acid which is known as carboxylic acid. Those are the ones which you can predict their boiling point or the melting point, which is depending on the number of carbons. But there are some other inorganic acids. So there's no such rule in general for acids and bases that can tell you this is higher or lower. Okay. But for organic acids, yeah, that is true, as we discussed previously in organic chemistry part. Yes, but we will see that. It is one of the examples. We will introduce, as a matter of fact, ammonia as a base when we discuss the Bronsted and Lowry acid base definition. Because if you go to the, anyways, I don't want to rush things. Let's take it on time. So for the bases, they have something like special about them, that they feel like soap. I mean, they have this, property of feeling in your hands like soap. If you ever been in the lab and you touch sodium hydroxide, for example, it is very slippery. You can put it in your hand and you feel that. Also, they have a better taste. The taste is better. You know what better is? Huh? لا هو مر better. لا ده okay, that's a different word. عمري سمعت اللاذع بس anyways. Yeah, طيب. بعدين the simple feeling will better taste. Also, they can use to change the indicator, as we mentioned, the litmus paper and so on. And they are also making aqua solutions. And when we do that, usually we have weak electrolytes, as that is strong or weak depending on the type of base that we have. If we have a strong base, then that will make a strong electrolyte. If it is a weak one, then that will make a weak one. Okay, so these are general properties, not necessarily to be memorized or anything, but just for your information that acids and bases, they do have distinct properties that are different from other materials, special about them. Okay, what is the first theory, which is put together by the Swedish chemist, which is Svante Arrhenius, he put the first definition of acids and bases, where he said that acids are hydrogen-containing compound. That's the first requirement. So acid should have hydrogen in there, and also that compound, whenever it is ionizes means split into ions, positive and negative, then in that case it will yield or produce a hydrogen ion. So we can summarize this by saying that acid, according to the Arrhenius definition, it is a hydrogen ion producer. Okay, it says a producer. This is very important because we said that it is going to yield that which is to produce. So we can say that acid in this regard is H plus producer. It has to contain a hydrogen in there. It's a hydrogen containing compound. What about the base according to Arrhenius? According to the Arrhenius, base are compounds that whenever they ionize, they produce hydroxide ion. So that is completely different. So acid, they produce H plus, and the base, they will produce OH minus. So that with that, we understand that we should have we should have a hydrogen in the acid, and we should have a hydroxide ion in the base. That's why, of course, this covers a good number of acids and bases, but that, of course, you will see that it will have a very limited number of material that can be done in there, or can be covered. So that is the first definition. Again, hydrogen is, or acid is a hydrogen ion producer, and the base is the hydroxide ion producer. This is the way it works. When we have aqueous solutions of acids and bases, or acids specifically, we produce what we call hydronium ion. What is this hydronium ion? It is the hydrogen ion that we produce from the ionization of the acid. It does not exist as it is. It does not exist only as H plus. Usually it will be combined with water to form what we call hydronium ion. So in this regard, if we have a hydrochloric acid that we put in water, theoretically we should have it like this: HCl to produce H plus and Cl minus. This is according to Arrhenius. HCl is a H plus producer, but we are saying that in that solution that we talk about, instead of having it as H plus only, it will be in the form of H3O plus. So the water here absorb that H plus and form what is known as the hydronium ion, H3O plus. Okay, and the Cl minus. So this is the aqueous solution of of an acid. Now, this is a list of different acids, as you can see in here. Judy was asking, this is the one that you were talking about, whether you can predict their boiling point, if it is organic acid, like ethanoic acid, butanoic acid, and so on. But for the, inorganic acid, that will be a little bit different. Anyway, what do you notice about these? HCl, HNO3, H2SO4, H3PO4, CH3OOH, H2CO3. What do you notice about these acids? Are they the same? How they are different? Then ما فيش حدا غيرك يا جودي جاوب. How they are similar and how they are different? Yes, that is similar by having an H, and that H has to be ionizable. In addition to that, they are different in the number of hydrogens that they have. For example, these two here, they have one hydrogen that they can donate. This one can donate 2. This one can donate 3. This one can donate 1. Of course, these are not. And this one can donate 2. So it depends on the type of acid. We may have different number of hydrogen in there. So all of them, they contain hydrogen. That is true. But that hydrogen has to be ionizable. And in addition to that, they have different. So we can classify the acids and bases based on, the acids are based on the number of hydrogen that they can produce. And we call that ionizable hydrogen. This is very important because according to the definition, that it is an H plus producer, and it will produce that whenever it is ionizes. Ionizes means to split into ions, plus and minus. That will happen only with the hydrogen that is ionizable. which is being able to be split from the compound into as H plus. So we have what we call a monoprotic acids. Those are the ones which can give only one hydrogen, like HNO3, HCl, and so on. But we may have something like sulfuric acid, which has two ionizable hydrogen. In that case, we call it diprotic acid. And if we have something like phosphoric acid, then we call it triprotic acid. So we have monoprotic, diprotic, and triprotic. That means they have different number of ionizable hydrogen. Whenever it is one, it is monoprotic. Whenever we have two, that is diprotic, and whenever we have three, that is a triprotic. Okay, is that necessarily that any hydrogen containing compound should be an acid? The answer is no. Why? Because we may have, it has to be, it's not only to contain a hydrogen, but that hydrogen has to be ionizable. How can we differentiate between a hydrogen that is ionizable and the one which is not ionizable? The one which is ionizable should be connected into a highly electronegative atom. Why is that? Because regardless of the atom, here's the hydrogen. It is bonded to an X. Now this X, we are saying here that has to be highly electronegative. Now I assume that you still remember what electronegative is. Electronegative means that the electrons are pulled more toward that atom. So eventually this kind of bond here is covalent, but it has a partial positive here, a partial negative there, which will make it ionizable hydrogen. It's easy to get rid of, to split, to break that bond and ionize it into H plus in that case, and X minus. That's what we mean by ionizable hydrogen. So again, here the example of hydrogen chloride. We have a partial negative here and a partial positive there. Because chlorine is highly electronegative, as you know, then in that case, having partial positive, partial negative, we can break that or ionize that compound into H plus and Cl minus. So this hydrogen, we call it as ionizable hydrogen. Now let's take some example where it is not ionizable, like methane gas, for example. If you consider CH4, it has 4 hydrogen, but can we consider methane gas an acid? No. Why? Because the hydrogen is bonded into carbon, and carbon is not highly electronegative. Okay, so that is a normal. As a matter of fact, the difference in electronegativity between carbon and hydrogen is very close. Hydrogen is about 2.1 and the carbon is something similar. So this is a no ionizable hydrogen or a non-ionizable hydrogen that can be found. We may have some compounds that contains both, and that is the what we call organic acids. Organic acid or carboxylic acid, as we discussed them before, they do have other hydrogen that is non-ionizable, and they have only one that is ionizable. The difference between these 3 hydrogens and this hydrogen is the fact that the hydrogen that are bonded into carbon, they are not ionizable because carbon is not electronegative. But the ones which is, or the one which is bonded into the oxygen is ionizable hydrogen. So only one hydrogen in the case of the ethanoic acid is ionizable. So in this case, ethanoic acid is classified as monoprotic acid because it has one. As a matter of fact, all the carboxylic acids are monoprotic. That monoprotic, diprotic, triprotic kind of definition usually used with inorganic acids like nitric acid, sulfuric acid, hydrochloric acid, phosphoric acid, and so on. But anyways, it's good to know that this is the monoprotic. This is the only hydrogen which is highlighted with yellow, is the one which is ionizable and can be given off or can split from the compound in aqueous solution whenever they are in solution. All right, moving into bases, we do have a list of known bases, like sodium hydroxide is very popular, potassium hydroxide are very popular too. The solubility in water of these are very high, which means that they are easily ionizable into Na plus OH minus. Okay, but these ones, which is calcium hydroxide and magnesium hydroxide, they are very low I mean, the solubility is very low in water. What is the difference between these two and these two? They're different by the metal. The metal here is from group 1. That is group 1, potassium, sodium, and lithium, and cesium, and those guys. And this one are from group 2. And that is typical. I mean, forming a 2+ cation, it will be difficult than forming a +1 ion, because that is easy to make. Yeah, this is something that we already discussed before, but it's good to notice that's something that we know. All right, so sodium hydroxide, for example, it is an ionic solid. It is made from positive and negative. So when you put it in water, it will split into sodium plus and OH minus. So according to the Arrhenius, which is a base, is a material that can produce a hydroxide ion when put in solution, is typically, this is Arrhenius base. Now, one other properties which is known about bases in general, and especially sodium hydroxide, that is highly caustic. Highly caustic, that it will dissolve hard material. And this picture here, you can see that this is the material that we usually buy to unplug the sinks at home. When you have your sink or your whatever shower is blocked with your several types of dirt, then the only way to do that is either to put your hand in there or buy some of those materials, and then you dump it in there. That bottle over here contains sodium hydroxide, which is a caustic material. Caustic material means that substance that can burn or can eat away the other material, like the dirt and air and whatever is clogging the drains. And the way it works is by ionization, by forming the Na plus and OH minus. Now, how it eats that is a different story, because we don't know what other materials are there. The other strong kind of base is potassium hydroxide. It is also the same way. It will be ionizes into K plus and OH minus in there. The solubility is very high, so expect it to go into completion. Elements from group 1, if you remember, when we talk about sodium, for example, if you take a piece of sodium and you throw it in water, it will make a flame. The reaction is very, very strong and very vigorous, to the point that it will make a flame, which is, again, due to the vigorous reaction between the two. When they react like this and make the flame, they produce sodium hydroxide and hydrogen gas. The flame is coming from burning the hydrogen, basically. That's what the one which is produced. But the reaction is very strong, very aggressive, and it will produce sodium hydroxide. So this is one of the methods of preparing sodium hydroxide as a base. Now, if you consider these two, their solubility is very low, and that's why they are safe to be used in this kind of product. This is what they call it, like Maalox and this kind of material that can be used to treat the acidity in your stomach. If you have an acidic stomach, usually you take 1 spoon of that liquid. That liquid actually contains either calcium hydroxide or magnesium hydroxide. Now, we just said in a minute ago that we can use sodium hydroxide as a caustic material. So imagine that this is made from sodium hydroxide and you put it in your mouth, it will eat up your throat, right? Because it's a caustic material. As a matter of fact, if you put your hand, it will, it will affect it. So, but in the case of calcium and magnesium hydroxide, because their solubility is very, very low, they will not be ionized in a very high point, and that's why they can be used or safe to digest, safe to take. These compounds are not very soluble in water, and because of this, the low solubility of magnesium hydroxide can allow us to use them in a suspension safe to consume. Suspensions هذول اللي هم like this compound. أنا مش شايف شو اسمه. هذا milk of magnesia. This is one of the products, but there are many other products that Gaviston. This is the one that we have usually here. You never use it? ما شاء الله معدتك قويه. اوكي، جافستون هذا اللي بيجيب دعايته يكون واحد كانوا يدخل جوا المعده وبيحط ها yeah, it's just a cartoon يعني sometimes مش واحد شخص، لا لا، بدخل جوا زي تبعون الفاير ديبارتمنت وبرش شويه جافستون، بعدين بصير يعني في طبقه من هذا to prevent the acidity or the the acids to come back to your throat. Okay, so that is the definition of Arrhenius, and as you can see, we have seen about 4 bases and a group of acids that can be defined easily as per that. But then later on, these two scientists, they found that there are some other materials that they have the same properties of acids and bases. They do change the litmus paper, they are caustic, they are better taste, they have all these properties, but they cannot be defined by Arrhenius. If you take an example of sodium carbonate, for example, sodium carbonate is a base, but according to Arrhenius, where's the hydroxide? We don't have hydroxide in there. So that's why those guys decided to put a new definition that will include some other materials that they do have acid-base properties but cannot be covered by Arrhenius. Like, as we said, and ammonia, you ask about ammonia. Ammonia is a very well-known base. Also, ammonia does not have a hydroxide ion. So how can we define sodium carbonate or ammonia as a base according to Arrhenius? There's no way that you can do that. We have to modify the definition, or they had to modify the definition in order to still include the previous materials, but it will include other materials like those to become included in the definition. So that's why they put a new definition which says that acid is a hydrogen ion donor. So there's almost no difference in the definition here in regard of the acids, that it is in there, it is containing hydrogen, and it is produces hydrogen ionizers. Here we call it hydrogen ion donor. So still it is producing hydrogen, but the problem is with the base. The base is completely different in this case. In this case, it says that a base is a hydrogen ion acceptor. It is not a hydroxide ion producer, but rather it is a hydrogen ion acceptor. In that case, it will become easy to include ammonia and sodium bicarbonate in there, because when they react, they basically accept a proton, and in that way they act as a base. So that this theory also include all the others. For example, if you consider hydroxide ion or sodium hydroxide, it will accept a proton. So sodium hydroxide still as a base as per the Bronsted-Lowry, but sodium carbonate or ammonia cannot be fit in Arrhenius, but they can fit in here. So all the materials that were defined as per Arrhenius, they are actually can be fit into under the Bronsted-Lowry theory, but also with other more material. So it includes all other material that cannot be defined. Let's take ammonia as an example. We'll dissolve ammonia in water. What will happen is that the water is the one which will produce an H+, and that will accept it. So what we'll produce is ammonium ion, and we will produce a hydroxide ion. So in that sense, in that regard, you can take a look at the ammonia as being a base, because it accepts a proton from the water. And water in this case is acting as an acid by donating a proton. So according to the new theory, which is Bronsted-Lowry, when we have acids and bases, usually they should be combined together. So we have acid and we have a base. So acid and base react with each other. One of them is donating hydrogen, the other one is accepting a hydrogen. Like the water in this case is acting as an acid, and this is acting as a base, because this one is donating the hydrogen, this one is accepting the hydrogen, and we produce the ammonium ion and the hydroxide ion in the other ion. So with this definition, now we can include the ammonia as being Bronsted-Lowry base. Although if we can only use the Arrhenius, it's not. It's not defined as a base. So ammonia is acting as a base and water is acting as a, we have to specify, we have to say that is Bronsted and Lowry acid, because or otherwise you have to say this is Arrhenius acid and so on. This to make sure that it is as per the definition. Okay, they notice also one other thing, which is the fact that if they, in that solution, which is made from ammonia and water to produce ammonium and hydroxide, if they do increase the temperature a little bit, they found that they can smell ammonia. What does that mean? This means that if you increase the temperature, if you rise the temperature or heat it up, what you do is you are encouraging the backward reaction, which is ammonium is being converted into ammonia and producing ammonia. So if we look to the forward reaction, it is ammonia here is acting as a base and water is acting as an acid, right? What about the backward? When we do the backward, this one is the one now which is accepting the hydrogen. So this is a base, and this is acting as an acid. But that acid, which is ammonium, is related to the ammonia. The way it is, I mean, it's not an acid. That ammonia is a material that has been used everywhere. So that is a base that can be manufactured and so on. But the ammonium as an acid, the presence of the ammonium as an acid is related to the ammonia reacting as a base. So these are connected. They are, the existence of these two are together. So that's why instead of calling this an acid, we're going to call it a conjugate acid. What is the meaning of a why we call it not an acid, we call it conjugate acid? Because it is, being an acid is conjugated to another base. So we have a base and a conjugate acid. We have an acid and a conjugate base. So these are pairs like that. All right. So whenever we are dealing with Bronsted and Lowry acids and bases, usually we form, conjugate pairs that is relating the acids and bases together. So the presence of ammonium is related to the ammonia as a one like that. So reversible reaction have two sides of the bases. So we have base, acid, conjugate, base. Why we call it conjugate again, Ya Judy? Because the presence of this is related to a base. So every conjugate acid has a base, and every conjugate base have an acid that is combined to it. We're not going to have this unless we have the water acting as an acid by losing a proton. Whenever it loses a proton, it will form the hydroxide. So that's why it is a conjugate base. Why it is a conjugate base again? Because it is related to the formation of acting, or the acting of water as an acid. All right, so NH4 is an acting a conjugate acid for the base, and OH minus is a conjugate base for the acid, which is water. We can use other examples after we see this definition, that we should be able to determine acid-base conjugate pairs. So a conjugate acid-base pair consists of two ions or molecules, because we notice that we have ammonia and ammonium, water and hydroxide ion. So either it is going to be ions or molecules related by the loss or gain of one hydrogen. Yes, ammonia and ammonium, which is, this is a base, and that is a conjugate acid. What is the relationship between them? It is a hydrogen ion, right? It's a gain or loss. Here it is a gain, and this way it is a loss. So any two compounds or molecules or ions that are related to each other by gain or loss of a hydrogen is called a conjugate acid-base pairs. All right. So let's see some examples based on that. This is again the same example. So these are related as one pair, which is ammonia and ammonium, water and the hydroxide. Let's consider, having HCl dissolved in this. You remember when we defined hydrochloric acid as per Arrhenius, it is the one which produces H+. but that H plus will be combined with the water as hydronium ion, right? So that hydronium ion is, as a matter of fact, is a conjugate acid of the water acting a base. Oh, so here the water is acting as a base, while here the water is acting as an acid. This is something to be defined in a minute, and that is these kind of material that can act as an acid and sometimes act as a base, depending on the other partner. Okay, that is, we call them amphoteric material. Amphoteric materials are the ones which can act as an acid and base. Anyway, let's focus on this. We will come to that definition again. So we have the pairs again. We have an acid with a conjugate base, that is the Cl minus and the HCl. They are related by the gain or loss of hydrogen. And the water and hydronium ion, also the same thing. They are ions or molecules that are related by the loss or gain of hydrogen as well. Okay. So if we want to try this example, this is sulfuric acid reacting with water to produce hydronium ion and hydrogen sulfate ion. Now he's asking, use the figure to identify the two conjugate acids and base. If this is an acid, of course, and in that case, water has to act as a base. Has no choice. When you put water with acid, it should act as, so this is an acid, we know that. Let's use this one. And this is as a base. What is this one is produced from? That is produced from this one. So if that is a base, then this is going to be a conjugate acid. And this one will be our conjugate base, right? So this is conjugate base, this is conjugate acid, this is a base, this is an acid. The way you can determine those is look at the ones which are related by gain or loss of hydrogen. Yani, giving a hydrogen will give us this one, removing the hydrogen will give us the other one. These are acid-base conjugates or conjugate pairs. This is a list of acids and bases and their pairs. For example, HCl along with Cl minus, H2SO4 with HSO4 minus. But that one also, as you can see here, this can act as an acid here, right? Because it can give one more hydrogen. So this is a conjugate base, and also here it is acting as an acid again in order to form the sulfate. So those materials that appear in both sides, as a matter of fact, are the water. Water is here as a base and water is here as an acid. If you consider hydrogen iron sulfate and the hydrogen iron sulfate, these are appearing in both sides. Also, you can see the hydrogen carbonate and hydrogen carbonate, they appear in both sides. Whenever you can have something that acting one time as an acid and acting the other time as a base, we call that an amphoteric material. The water is the most famous one, but there are some others that can be defined as I mentioned over there. So a substance that can act as either acid or a base, depending on the situation, that one we call it amphoteric material. So water is an amphoteric. The reaction with hydrogen chloride, water accepts a proton to form, therefore it's a base. When reacts with ammonia, it was what? It was given a hydrogen, that's why it was acting as an acid. So water here reacts with hydrochloric acid, then it will become a base. Whenever it reacts with ammonia, which is a base, it will act as an acid. As I said, it is very important for you to know that it is not only water, but as I mentioned, all the ions that are produced from a multi-protic acids. Yani like hydrogen sulfate ion, it is here and it is there. Again, I'm mentioning that. This one and that one. So it's not only water that is amphoteric, but some other ions that's produced from a multi-protic acid, yani diprotic or triprotic, like for example, which is not listed here, if you have phosphoric acid, for example, it will produce two amphoteric material. The first one by losing the first hydrogen, and the second one by losing the second hydrogen. And the third hydrogen, of course, is acting as an acid, the phosphate ion. Okay, so now we left with the last definition, which is about the Lewis acids and bases. Even with the Bronsted and Lowry being broad and covering, many other materials, still there are some other materials that yet are not covered as acids and bases. That's why Gilbert Lewis came and he put another definition for that. He relates that to the electrons rather than to the protons. He said that an acid that accepts a pair of electron, and a base is the one which donate a pair of electron. So it has to be a pair of electrons that are donated or accepted. Now, if you remember, in the case of the Bronsted and Lowry, the one which was a donor was the acid, donating an H plus. Here, it is the one which is accepting the two electrons. And the opposite is that the base is the one which is given. This definition is more general, and it includes all the material that can be defined by Arrhenius or the material that can be defined. So as I said, you can use or you can draw that as Arrhenius is here, covering some number of acids, let's say these. And then we have the Bronsted and Lowry, which have some other materials in addition to the Arrhenius. And then we have the Lewis acids and bases, which covers new materials in addition to the Bronsted and Lowry and in addition to the Arrhenius. So that's why it's a more general definition that we have in there. طيب, then Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. Remember the covalent bond? There was one special type of bond that we talk about at that time, which we called coordinate covalent bond. Remember? What is a coordinate covalent bond type? It is, well, covalent bond is made from two electrons shared between two atoms. Coordinate covalent bond, the two electrons are coming from one atom. That's what it is. So as a matter of fact, the Lewis acid is the one which is accepting a pair of electrons in order to form a covalent bond, and the Lewis base is the one which is donating that. So we should have acids and bases. Lewis acid and Lewis bases, they interact with each other. And one of them is given a pair of electrons, and the other one is accepting that. The one who can donate that should have it. Yeah, nobody can give money unless you have money, right? So, and the one who is accepting that must be in need. So the way we also can identify the Lewis acids and Lewis bases by the fact that the base should have lone pairs that's sitting in there, and the acid should be electron deficient, that they are in need of something like that. Like, for example, if you consider the reaction of hydroxide ion with an H plus, both of them, they can be defined by Arrhenius. Both of them, they can be defined by Bronsted and Lowry. But now we're going to look at it from a different angle. When they react with each other as a base and an acid, the two electrons that are given from the hydroxide ion to the hydrogen to form a covalent bond. Okay, so in that case, it is the hydroxide ion is acting as a Lewis base because it donates the pair of electrons, and the hydrogen is the one which is accepting that as an acid. Okay, that is something. A second example, if you wish, is if we mix ammonia dissolved in reaction between Lewis acid and Lewis bases. It happens when ammonia dissolves in water, right? You have ammonia plus H2O. How they gonna act as acids and bases? What? Well, no, Lewis acids and bases. We're talking about electrons. So the electrons from here are going to be donated into something as an acid. So what we will see is that according to the definition, we have the Arrhenius as H producer, and that is an OH producer. If we look at the Bronsted, this is an H donor, that is an H acceptor. According to the Lewis, then this electron pair acceptor, that is a electron pair donor. All right. So let's move on to see this example, which is ammonia with BF3. Now, you know that all the boron compound, as a matter of fact, the boron has how many electrons? It's in group 3, so it has 3 electrons, and it's forming something like this, right? Now, the boron here is not satisfying the octet field because it has only 3 pairs around it. But that's why we call it an electron deficient. While ammonia has a lone pair, so these lone pairs will be given that to form what we call a covalent bond. So if you move into this picture here, this is what will happen. These are the lone pairs that's coming from the ammonia, will be given to the boron fluoride. So boron fluoride in this case is acting as an acid. What kind of acid? It's a Lewis acid. And this one is acting as a Lewis base by donating a pair of electrons. And they will form this kind of bond, which is again a coordinate covalent bond because it's coming from one side, and that is from one. So ammonia acting as has an unshared pair of electrons that can be donated, and the boron atoms accept the donated electrons in that case. So Lewis acids can donate pairs of electrons. Ammonia is defined as a Lewis base, and boron trifluoride is acting as a Lewis acid. Okay, so that is the end of that. Let me just summarize again that we can use that table over there. This is what we're gonna use. Yep. This one here, this is summarizes the whole lecture. Arrhenius is a producer of hydrogen as an acid, producer of hydroxide is that. Bronze is H plus donor and H plus acceptor. Lewis is about a pair of electrons that are donated by the base and accepted by the acid. But this definition of Lewis covered all the material that before and so on as the circles that I was drawing to you. Okay, so that's the end of section 1, and that's the end of the week. And you have a homework waiting for you from Tuesday that you have to do before, inshallah, before Saturday. All right. Which that's the other one. Well, as a matter of fact, next weekend we're going to have the review homework, as I told you about. The review homework is going to be, again, it's like an exam. It will be fixed in time and also fixed in the amount of minutes that is provided. Yani we're going to give 50 minutes, and that will start at, for example, we'll agree on a time, like on Friday at 9 p.m. and we'll close at 10. Okay, that is for you to practice a real exam. Okay, that will be next weekend, not this week. Okay, thank you guys, and have a nice weekend.